G will therefore be positive. It will consist of the standard state term plus the component that accounts for where you're at in the cell. So there's a thermodynamic driving force in the reverse direction. And this is with, say, Q is just hypothetically, Q is 200. And if Q were 2,000 instead of 200, right, this number would be a lot bigger. There'd be a lot bigger driving force to go backwards. Right? If Q were 20, and equilibrium is at 19, then how much of a driving force is that? Practically nothing, right? So the magnitude of the driving force becomes the important parameter in deciding, in looking at which direction you, not only which direction you go, but how strongly the driver is to go that way. So if we look at this in the context of glycolysis and gluconeogenesis, right, here are reciprocal pathways. And so in these pathways, we have 7 enzymes that are reversible and 3 that are not. Right? So the 3 that are not are at step 1, step 3, and step 10. And we talked about how in steps 1 and 3, the reverse reactions are just phosphatases, the gluconeogenesis reactions are just phosphatases. The same, different enzyme, but single one step. And here, the reverse reaction is more complex because it has to go through the mitochondria and a couple of different new enzymes, as well as a moving of the reducing equivalents from the mitochondria to the cytosol in the form of NADH. Right? So that NADH can be replenished for this step here to go this way, the loop going on. Right? So this is what it looks like sort of in terms of the pathway. And then if we look at the condition in the cell for different kinds of cells. So here's a liver cell and here's a heart cell. Right? So this is giving you the Q value in the cell. Here are all the enzymes in the pathways. And here's delta G0 prime, the standard state number. Here's the standard state equilibrium constant. Okay. Here is the delta G in vivo, and here is the mass action ratio in vivo. And here is an assessment of whether the reaction is near equilibrium in vivo. And so for all the reactions that are reversible, they are near equilibrium in vivo. So aldolase, triphosphate isomerase, mutase. Here they've combined these 2 enzymes for some reason, reversible. Another isomerase reversible, the phosphatase reversible. So the reversible reactions are maintained in the cell at a Q level such that they're near equilibrium. Okay? So if it was a mutase, the Q that would be maintained in the cell would be already somewhere around 19. So in the case of a mutase, it's not on this list, but if you think of the mutase from G1P to G6P, and the metabolite concentrations of G1P and G6P are such that you already have something like 19 times more G6P, or maybe you have 25 times or 15 times more. Right? But there's the driving force for that is pretty small to go the rest of the way to 19. Right? So if it gets a push in either direction by way of either metabolite increasing in concentration, it's going to go in the direction that it's told to go in by virtue of something that's linked to it. Does this make sense? Because it's near equilibrium now. If you have G1P and G6P near equilibrium, and all of a sudden you get a lot more G1P because of something else that happens, then you're going to go G1P to G6P. The driving force is immediately going to be that way, because it was at equilibrium to start with. So that's the idea here. So anything that's near equilibrium it doesn't care which way it goes. And it's also a reversible enzyme. So it can go either way just by virtue of what it's doing as an enzyme. Right? It's binding to substrates, it makes products. Okay, that's fine, I'll do that if you want me to. Oh, did you want me to bind the products instead by giving me a lot more product? Okay, I'll do that if you want me to. I'll go back the other way. Right? So those 7 enzymes are just happy to do whatever. And the Qs in the cell are maintained by virtue of the regulation on different enzymes in such a way that their Q's are near their K's. That make sense? The Q's are neither their standard state K's. In other words, what the molecules intrinsically where they want to go in terms of their thermodynamics, that's already where they are by virtue of regulation of other enzymes. And that's just what the metabolite concentrations are. So here in glycolysis, it doesn't give you the actual concentrations, but it gives you what the mass action ratio, the relevant ratio of the concentrations are in these different tissues. Right? So then we have those, and then we have the ones that are out of equilibrium, which are the ones that are going to drive stuff. Okay. So Q is not equal to K prime EQ for example, hexokinase, phosphofructokinase, say phosphofructokinase 1, because next class we're about to learn that there's a PFK2. Pyruvate kinase. And so these guys are regulated. And for the other 7, are reversible, and Q is approximately the same as K prime Q. So no driving force, so little or no driving force. And so they'll go either way. Okay. So let's look at PFK, just as the example. Right. So this is the reaction that it does. Okay, so ATP plus fructose 6-phosphate in the forward direction, ADP, fructose 1,6-bisphosphate. Delta G0 prime is minus 14.2. So that's just intrinsically where those molecules want to be, from which you can calculate a K. From that, it's about 315. The chart, by the way, says the K is 1,000, but that's not right. I don't know why that chart is 1,000. They must have pulled numbers from different places without bothering to check if they were consistent. But 1,000, 315, not that worrisome, just in case you note that. And then from the measurement in the cell, right, in the heart cell, so we go in and actually measure it. Measure the metabolite concentrations and calculate Q, just from the mass action ratios. Q is 0.03. Yeah. So because Q is 0.03 in that condition, right, it's in a situation where Q is 0.03, so these are low and this is high, right? Now it's already favored to go forward pretty strongly, and now it's going to be favored even more, right? So the one thing to see is that the cell has contrived its metabolite concentrations in this case to come up with a situation where the driving force is even stronger than it would have been at steady state, which was already pretty good, but now it's even better. Right? So you can plug these numbers in. Right? RT is 2.47. Minus 23 is what's written in the table in the textbook. The only difference in the table in the textbook is this number is written as 10 to the 3, but who knows why they did that. Okay, any questions so far? So this is just another example of the application of this equation. Okay. So what are we going to do about